For this video, we are going to be starting Chapter 8 on association claims. Now, a lot of association claims are actually correlations, which you may be familiar with. And some of this was introduced in Chapter 3, and we didn't really pay much attention to it at the time as far as what's a positive and negative correlation. So we want to do that now, and if you need a little more reading, because you love to read, go to Chapter 3 to look at that. But let's start by, there is a worksheet on Blackboard with correlations. Here it is, and it's got some examples up here that we're going to be looking at. Let me start first, though, with a couple of slides. Okay. So, get my slides up here. Okay. So Chapter 8 is about bivariate correlations. All that means is there are two variables. Now the key here is association claims are always when you're dealing only with the measured variables. So if we have two measured variables, things that are just kind of true about you and we collected data on, we're doing an association claim, a correlation. Now Chapter 9 is actually about when you collect data on multiple variables, still all measured variables, and you're looking for relationships. And this gets into multiple regression, and we actually are not going to cover this for this class. Hopefully you'll have in your stats class, or if you take 395. But for this, we're just going to stick to a simple correlation with two measured variables. And what you'll see here on the slides are, on this side, you're going to see a scatter plot. Now this on the left, this graph, is when you have two continuous variables. Now a continuous variable is something that can just vary along a continuum. So your height, your weight, your age, your GPA, how much you like something on a scale of 1 to 7 or 1 to 10 or 1 to 5 when you're putting down your opinion about how strongly you feel about something. Well, continuous variables, there can be values all along that continuum, okay? So here on the left, we have a well-being scale, okay, that can vary. We also have percentage of time that you're in deep conversation. So these are things that can vary along a continuum, and that means every dot here is a person, one of our participants in the study that we collected data from. And we're going to put that dot where the coordinates for the score of their percentage of deep talk and their score on the well-being scale. Okay, so each person here. And what correlation tells us then is it goes, okay, what if we were to figure out kind of with all of these data points, this line is a best fit line. What if we were to, kind of draw a line through here that shows sort of the trend of the data we have? I mean, as you kind of see, as people increase on the well-being scale, the percentage of time they report being in deep conversation also increases, tends to increase. This is like a trend, right? The dots kind of seem to go up a little bit to the right. And that's what this line is showing us. And the correlation coefficient, which will be R, is going to be a number that varies from -1 to 1. Now, as it gets close to 0, a correlation of 0, let's see if we means that, let's see, would be something like this, where there's no trend. This, as the scores go up, you don't necessarily get higher on the scores up here, okay? If we were to look for a best fit line here, it would be pretty flat, okay? Let's go back. I'm kind of getting ahead of myself. So let's do the positive negative part. So if we look at this graph here, as we increase on the x-axis, the values increase. The values on the y-axis tend to increase too a little bit. It's kind of a weak correlation. But the first thing we want to do is label any relationship as positive or negative. And that's going to be how do the variables move. So if we're looking, let's say, the taller you are, the more you weigh. Okay, those things tend to go together. So as you get taller, you tend to weigh more. In this, the variables are moving in the same direction, and we call it positive when they move in the same direction. Now, it doesn't mean they're moving up necessarily. They are, but I could just as easily say the shorter you are, the less you tend to weigh. So both these variables could also decrease together, and we still call it a positive correlation. The term positive just tells us that the variables are moving in the same direction. Because it's always true, if this goes up and this goes up too, well, then if this goes down, this is going to go down too, right? They just kind of have a relationship where they move together. Now, sometimes we'll have a relationship whereas one thing increases, the second variable we measured tends to decrease. And this is a negative correlation. It just means they're moving in opposite directions. It may help now to look at this worksheet that you need to do. And so either print it out, or you could look at it on the screen, I guess, or have it open on your laptop. I want you to go through A through J and label each as a positive correlation or a negative correlation. Now, all you are looking for here is at which direction the two variables go. As one goes up, does the other also go up or go down? Do they move in the same direction, then it's positive, or in different directions, negative? Let's do the first one together. It says the more rooms a person has in their house, I'm going to get my mouse up here. Okay. The more rooms you have in your house, and the more rooms, look at my hands over here, the more rooms, the more pairs of shoes are likely to own. Okay, so what I see here is variables moving in the same direction. So that means we call it positive. Okay? So we'll do the second one together as well because it's kind of funny. It says the more class days you miss, I'm counting your absences. Then as absences increase, the lower your grades are likely to be. So as absences go up, grades go down. Opposite directions, we call it a negative correlation. Now this is a good example where whether or not a relationship is going to be a positive or negative correlation really depends on how you measured your variables. In this example, we measured number of absences. Somebody else could have measured the number of days you were in class. And if that were the case, it would say the more days you're in class, the higher your grades. Or I could say the fewer days you're in class, the lower your grades. Well, both of these are positive correlations. But in B, that's not how I measured my variable. I counted absences, not days present. So it changed whether it's negative or positive. So be careful about that. All right, so I want you to pause the video. I'll leave it up, so if you want to just pause and you can look at the examples in front of you. And just go through A through J and label it negative or positive correlation. Okay, so go ahead, pause for real, hit pause, and then come back. Did you really do it? Are you sure you didn't do it? Okay. This is where the learning takes place. So I want you to push that pause button, do it, come back. Okay, are you sure? Okay. Now, I am not actually going to give you all of the answers. We'll just hit one or two more. And then if there's something you have a question about and you're not absolutely 100% sure on the answer, if it's positive or negative, I want you to go to the Your Questions blog and slap that puppy up there and go, I think this one is negative because, explain it, and then you'll get some feedback, okay? But let's see, what else do we have here? Well, let's look at G. G. The more Mozart the baby listens to, the higher intelligence scores. By the way, that is totally false, okay, just so you know. But we have more Mozart, higher intelligence. Moving in the same direction, positive, okay? We could have written that the less amount of Mozart in your baby's life, the lower the IQ. Still would have called it a positive correlation because the variables are moving in the same direction. Let's see, what else? Well, F has fewer friends, more likely to have symptoms of depression. Opposite directions. What do we call that? All right, let's go down now to the bottom and let's talk a little bit about strength of the relationship. Actually, I'm going to move back over to the slides for this. So we have the possibility of having, I think it's bigger, okay. All right. Okay, here's my correlation coefficients. Now the range is, they can go from -1 all the way up through 0 up to 1, the number of R. And there are actually at least 2, I know, but a few different kinds of correlation coefficients. Pearson's correlation coefficient is R, which is the most common. There's also Spearman's, which is, I think, an R with a little S and other things. But for now, just Pearson's R. And Pearson's, this number is going to get spit out from the equation where we put in all our data. Here's your R. Now, the negative sign or the positive sign, all that tells you is the direction it's going. All it tells you is, are these variables moving together in positive, or are they moving in opposite directions? Now, as far as strength of relationship, how tight is this relationship? The best you can be is a 1. It can be -1 or +1. A 1-to-1 correlation, you've probably heard that term before. What that means is there's an absolute 100% predictable relationship where if this moves a certain number of units, this moves another certain. So let's say if it were true that for every inch of height you had, you gained 5 pounds. So let's say that held true absolutely perfectly. And so if somebody was 2 inches taller than you, you knew they weighed 10 pounds more than you. If they were 3 inches taller, they weighed 15 pounds more. That would be to this 1-to-1 correlation. Now, there's almost nothing in the world that fits a 1-to-1 correlation. This is very rare, if it even exists. So, even if you get things like 0.9, 0.8, these would be hugely strong correlations. It would mean all the little data points from your scatter plot fall right on the line, okay, which is crazy rare and never sees. Now, what you see more is there's a little spread of your lines. So look at these down here. They scatter in your scatter plot a little bit more. And the more they spread and scatter away from the line, the smaller that number is going to be until you get all the way down to 0. And it's just spread all over the place. There is no relationship. You can't predict one thing from the other. It's just all over the place. Okay. Now, there is sort of this rule of thumb, Cohen's rule of thumb, that is in your textbook. And it's going to tell you, let's see, what is a strong or weak correlation? Let me go back to our worksheet. The rule of thumb, according to your book, is something around 0.1 would be weak. 0.3 would be moderate. 0.5 would be pretty strong. So there are some questions at the bottom of that worksheet. I'll pull that up again. About strength. So knowing 0.1, 0.3, 0.5, what would you think for some of these questions? Again, why don't you just pause it for a second and read through them and kind of see what you think. Come back. Okay, hit pause. Okay, we're back. That should have been fairly easy to do. One of the things, notice on question 3, get my mouse back here. I was trying to throw you on number 3. It says, a correlation of -0.7. Is that strong? Actually, yeah, it's kind of crazy strong, because I want you to remember to ignore the negative sign. Negative and positive doesn't have anything to do with how strong, tight that relationship is. It's just the absolute value of 0.7 that's important. This just says there's a negative relationship, so as one increases, the other decreases. Scatter plot's going to kind of go down to the right. But it's still a very strong relationship, so that's what that's testing you. Now, another thing to point out, look at this one. I kind of want to change this, let's see, to 0.1. This domestic violence example. It says, okay, you're measuring something, and unemployment rate. As it goes up, domestic violence also tends to rise. What if that correlation was 0.1? Is that strong? Well, according to our rule of thumb, it's weak. But the question then is it important? Well, think about this. Is domestic violence something that's just largely due to unemployment, or are there other factors that come into that behavior? There are other factors, right? What people have experienced, maybe growing up, if there's personality, how they were parented, unemployment, could be stress, could be substance abuse issues. There are a lot of things that will go into that behavior. So if I'm paying attention to just one, unemployment, but there's many other things that go into it, I'm not going to expect a real strong correlation because there's other factors, and I'm just looking at one little factor. Now, does that mean it's unimportant? Should I say, oh, it's weak, we shouldn't do anything? Or, what if this was substance abuse and I had this kind of weak correlation? But could I still do something? Could I, if I address substance abuse issues or I address unemployment, doesn't mean domestic violence is going to disappear, but would it decrease some? You know, could I have a positive impact somewhere a little bit? Well, then it may still be important, even though the number is kind of on the weak side. That's okay. All right, I want to go back to our slides again for a second and kind of see. We're doing more of this tomorrow or today if you choose to keep going. Here, let's just do a little test here on this slide. Here's some data. Is this a positive or negative correlation? Well, as the number of missed days increases here on the X, what's happening to the values of Y? They're kind of coming down. So it looks like these are moving in opposite directions. It's a negative correlation. Here's our pretty much zero correlation. Like this was a question out of these correlation coefficients at the bottom. Which one do you think is just going to most likely describe this scatter plot, where they're just all over the place? If you were to draw a line to show the trend here, your line would probably be pretty much horizontal, which if it's perfectly horizontal, it'd be 0. So out of these choices, 0.04 is probably the answer here. All right. Another thing about strength, look at these two examples. These graphs show the same prediction line. So if I'm going to draw sort of my best fit line, it's actually in the same place. This one's a little lower. But what I want you to look at here is these lines on the top, dots on the top, these data points, they cluster very closely to this best fit line. And in the bottom, they're more spread out. So the more they're actually close to the line, you're going to have a stronger correlation. A higher R, closer to 1 or negative 1. This is positive correlation, so it'll be closer to 1. And R is what we're going to also call an effect size. We haven't talked about effect size yet, but it basically tells you how big an impact is this, how strong a relationship is this. And again, if it's a perfect 100% correlation, 1-to-1 correlation, all of these would be on the right on the line. Now they're not, but they're very close. So this is a strong relationship. It's a strong effect size. Down here, they're kind of scattered. So the R is going to be smaller. It's not as tight a relationship. There's still this positive, this trend, but it's much weaker. All right. So R does tell us how big an impact is this? How tight is this relationship? Let me see if there's something else we want to do. Well, this tells you, and you'll need to kind of read a little more detail in the book. But here again, we have two graphs. They probably have similar lines for best fit, but these are going to be clustered closer. These are more spread out. So out of these two, which one is going to have the higher R, the stronger effect? Well, it's going to be the one on the bottom because it's going to be close to its line, right? We do need to know sample size to know effect size. That's going to play a role in it as well. All right, yeah, let's do this one last idea. This is when we have outliers. Check this out here. We have outliers. Look at in the top graphs. So with this data on the top left, look at all these data points with the one outlier. And that would give us a correlation coefficient in R of 0.37, moderate, all right? Now look at that same data set, but we dropped the outlier. Look how the R falls, 0.26. Ooh, okay. So what this means is when you do studies with association claims, you need to inspect your data and graph it and see if there's something that's, an outlier, because that's going to skew your R. It's going to look like there's more going on than there really is. Same thing over here on the other side. But notice here, we got the same data set on top and bottom, except the top has an outlier. But the other thing about the right side graphs here is it's a smaller sample. There's not as many people in the sample. So what you see is with the outlier, we have an R of 0.49. We remove that outlier. It drops dramatically to 0.15. And so outliers have a much bigger impact on your data set when there's a small data set. If there's more people in your data set, the impact is still kind of a big deal. If I had 1,000 people down here and here, but one little outlier, when I took that out, probably wouldn't have changed it much. Okay, so sample size absolutely plays a role in effect size. Okay, I'm going to stop it now. I think you've pretty much finished the worksheet. So go do the reading, and then we're going to have another video that uses that worksheet again to talk about third variables and why we can't have causation from correlation. That'll be the next segment.